Hey, and welcome back. I'm hoping by now Unit 2 is being very kind to you, and you're saying to yourself, well, I hope the lessons continue like this because this is really easy. Because most of it is review from Algebra 1, but I'm just going to keep reminding you, this is really important stuff we're doing right now. It's work that you started in Algebra 1 that we really need to make sure that we are mastering, not only understanding completely, but really truly mastering this information about factoring, because you're going to use this in every math class you take from now on. So please make sure that you're really getting this, and if you're not, come and see me after school because it's really important that we hammer this down. All right, so 2.4 notes today, factoring the greatest common factor, and we're also going to be talking about the difference of perfect squares. So a factor, which is a noun, is an individual component of a product. So for example, 24. When I'm looking for the factors of 24, I tend to do them in order. So I say 1 times 24, 2 times 12, 3 times 8, 4 times 6, and as soon as I get to 6 times 4, I'm already repeating myself, so I stop there. So these are all my factors of 24. 1, 2, well, 1 is trivial, right? 2, 3, 4, 6, 8, 12, and 24 are factors of 24 because they all divide evenly into 24, or they all have another factor that when multiplied together equals 24. So understanding what the word factor means is really important before we start to factor. All right, so because this is what we're going to do now, we're going to actually use the verb form of this. So to factor means to rewrite a quantity as a product of its factors as shown above. So write all the factors of the following integers. So if we continue the same process that I showed you before, again, if I'm trying to find the factors of 12, I want to make sure I don't miss any of them. So that's why I say 1 times 12, 2 times 6, and then 3 times 4, and 4 times 3 is just a repeat because the commutative property allows me to flip them around. So those are all the factors of 12, I'm sorry. So 30, do the same thing. 1 times 30, 2 times 15. This is where your multiplication tables really come into play. You have to know those times tables. 3 times 10, 4 doesn't go in evenly, 5 does. 5 times 6, and then we start repeating, so we're done. Moving on to C, 16. 1 times 16, 2 times 8, 3 doesn't go in, 4 times 4, and we're done. And 36, let's start up here. I'm thinking we're going to have a few extras here. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 doesn't go in, 6 times 6. Then we're done. Okay, so that will absolutely come into play when we start doing factoring of trinomials, and we need to come up with numbers that multiply together to give us a number. So we will hit that skill one more time in this unit. So the exercise 2 says rewrite each of the following binomials as a product of an integer with a different binomial. So we're just doing the distributive property backwards. So 5x plus 10, we're going to look to see what we can pull out of that, what's in common to each one of those terms. So 5x and 10 is going to be, a 5 is going to be common, and basically what we're doing is we're factoring out or dividing out a 5 out of each term. So what's left over? X plus 2. And then to give it a quick check, if you wanted to, you would use the distributive property to say 5x plus 10, right? Loop, loop, 5x plus 10 gives us what we started with. So B, hopefully you're looking at that and saying, well, this is easy. This is 2 times x take away 3. 6x. Now 6 doesn't go into 15. It's usually the first thing, my first go-to is the coefficient in front of the x term. But in this case, the 6 doesn't go into 15 evenly. So we think about some of those factors, or the largest factor of 6, which is 3. And 3 does go into 6 and in 15. So factor out of 3. Again, we're going to factor out of 3 out of each one. And you're going to get 2x plus 5 left over. And we have the same situation with D. Again, 6 does not go into 14, nor does 14 go into 6. So we look for the largest factor of each one of those. So I start thinking about 7, though that doesn't go into 6. 2 goes in, but is it the largest? And the answer is yes, because 3 won't go in either. So 2 goes in. So factor out of 2, and it's helpful sometimes to do this, and we get 3 minus 7x. All right, so far so good. We're probably saying to ourselves, yeah, I hope the whole lesson's like this, because this is pretty easy. So this type of factoring is often referred to as factoring out the greatest common factor, or the GCF. All right, the greatest common factor can be comprised of numbers, variables, or both. So what we've done up in exercise 2 is only factoring out numbers, coefficients. So now let's consider when we have to go a little bit beyond that in exercise 3 and start looking for other factors of our terms. So for example, in A, we have 3x squared plus 6x. So just like in exercise 2, it's pretty obvious that we can pull out a 3 because 3 is going to be common to 3x. I'm just not just saying the 3 and the 6. But now, remember what this means. I have 3 times x, and I have 6 times x. So we're going to pull out or factor out the largest number of x's that is common to both of them. So in this case, because we have 1x here and I have 1x here, I can only pull out an x. So 3x parenthesis. Now again, it's also very helpful. Nobody's going to judge you if you do this. 3x and 3x. So 3x squared divided by 3x. Remember, one of those x's cancel. And I'm simply, and the 3's cancel, and I'm simply left with x. And then here the x's cancel and left with plus 2. All right? I wish I could hear you saying, yeah, I got this. So moving on to B. Sometimes I think the numbers are fairly obvious, at least to me they are. If I see 20, I see 5, and I realize 5 does go into 20, so my greatest common factor is going to be a 5. But then we also have to consider our x's, and again, I have 1x here and I have 2x's here, so I can only take out one of those x's. So divide each of these by 5x, and here the x's cancel, and I'm left with 4 minus, and then here the 5's cancel. Well, this could have canceled 1 and 4. 5's cancel, and one of these x's cancel, but I'm left with an x. So 4 minus x. Moving on to C, 10x squared plus 25x. Again, these are kind of all the same, but I want you to really understand how to recognize when to pull out those variables. So again, we can't take a 10 out here, but we can take out a 5. I'm tired of using green. Let's move to blue. So take out a 5. I can take a 5 out of each one of these. That's the largest. I can't take a 10 out of 25. And I'm going to take one x out. So 5x, and I'm left then with x plus 5. Moving on to D. Remember, at any time, please, if I'm going too fast, just pause. Don't think you have to keep up with me. So 30 and 20. Well, 20 doesn't go into 30, 30 doesn't go into 20, but I know 10 goes into both. So 10, I can't pull an x here because I do not have an x sitting here. So I'm just going to pull that 10 out. It's kind of tricking you a little bit with that one. And we're going to get 3x squared minus 2. So that one was just taking out a number, not necessarily definitely not a variable. All right, so exercise 4. Just going to move this around a little bit. Rewritten in factored form, 20x squared minus 36 is equivalent to. So write it down. 20x squared minus 36x Well, looking for that greatest common factor now, the nice thing is this is multiple choice. So if I look here, I can start looking and saying, well, I'll look for the largest number. So this, I'm going to start here with this 9. Does 9 go into 20 and 36? 9 goes into 36, but not into 20. Does 5 go into 20 and to 36? Nope, that's not it either. Does 4 go into 20 and 36? The answer is yes. So 2 also goes into both of those, but it's not the greatest common factor. We're looking for the largest number that goes into both of them. So we're going to say 4, but now we have one x in common. So when I factor out that 4x out of each term here, I get 5x minus 9, which is our answer here in number 2. Now, of course, if you didn't have multiple choice to help you with that, and you had to start from scratch, I probably started with that 20. And I would have looked at that 20, and I would have said, does 20 go into 36? So does 20 go into 36 evenly? And of course, you're going to say no, it doesn't. So then we look for the next biggest factor of 20, which is 10. Does 10 go into 36? And the answer is no. So then we go to the next factor of 20, which would be, let's see, 20 would be, again, go back to your 1 times 20, 2 times 10, 4 times 5. That's all you got. So your next largest one is 5. Does 5 go in? No. So basically we check this, we check this, we check this, and now you start going up. Now we check 4, and 4 definitely works. So I use this method right here so often to find my factors, and it's something that I really think can help you too. All right, and again, if you need help doing that, use your calculator. It might take you an extra 30 seconds to do it, but then so what? It's only 30 seconds. All right, so let's move on to exercise 5. Rewrite each of the following trinomials as a product of its GCF and another trinomial. So here we're going to be pulling out common terms to a common term to 3 different terms. So in this case, in A, we have 2, we have 8, we have 10. So I think it's pretty obvious that 2 is our GCF for our coefficients. Now, can we take an x out? That's right. You can't take an x out because I would be needing to have an x in this term, which I don't. So we're just going to factor that x out, which is 2 out of each one. And I get x squared plus 4x plus 5. Same thing goes for b. I don't have an x in every term, so I'm going to be just happy with taking out a 5 out of each one, because I look and see the smallest number, 5, and 5 goes into 20 and 10, so I'm done. 5 times 2x squared minus 4x plus 1. Now beware. Notice how I have 3 terms in here, and I have 3 terms in here. That's what I need. So don't say that 1 just cancels. Remember, when you're dividing everything by 5, a lot of people will forget about that last term, and they say 2x squared minus 4x, and they forget about the plus 1. But 5 divided by 5 is 1. So now we move to C. And in C, we can see, the pun. All right, in C, we can see that we have an x cubed, an x squared, and an x. So here, if I look at the 8, can I take an 8 out? Does 8 go into 12 and into 20? No. So the next largest factor of 8 is 4. And 4 does go into 12 and 20. So we're going to take out a 4 and an x. So when I do that, I'm left with 2x squared minus 3x plus 5. And very similarly, we do the same thing in D. Although D, the same thing happens with this 6. I look at this 6. Does 6 go into 15 and 21? The answer is no. So the next largest factor of 6 is 3. Does 3 go into 6, 15, and 21? And yes, it does. So when we come here, we're going to take out a 3 and an x, and you get 3x parentheses. Now remember, I have 3 terms here. I'm going to have 3 terms in here. So I'm going to have 2x squared plus 5x minus 7. Pause if you need to take a little time to write some of this stuff down, and then we'll start talking about conjugate pairs. So conjugate pairs are two binomials that have the same first and second terms with different signs between them. Notice that it doesn't really matter which one comes first. So for example, we have x plus 4, x minus 4, 2b minus 6, 2b plus 6, and a squared b cubed minus 3c, and a squared b cubed plus 3c. And of course, when there's nothing in between, the operation is always multiplication. So exercise 6 says, let's multiply the following conjugate pairs, and if you notice a pattern. So let's take a look at this. I don't want to show you the pattern yet, although you have it on your paper. All right, so we have, if we're going to use the FOIL method or use the box method, we get first, which is x squared, plus 5x, minus 5x, minus 25. So I get x squared. Notice that these cancel out, minus 25. How about the next one? 9 times 9 is 81. 9 times positive a is plus 9a. Negative a times 9 is negative 9a. Notice how we always put the coefficient first. Consistency is helpful when we're writing down terms. And negative a times positive a is negative a squared. So this one I set up a little bit differently, but it's still okay. Still set up the same way because negative a and a positive a cancel out, and we get 81 minus a squared. Notice order matters. Notice how we started with the 9 here, and we start with the 81 here. You can't just switch them around. The commutative property does not work through subtraction. It only works through addition. All right? Because, for example, you can't say, let's see, where can I write this? Like if I say 10, I want this color, 10 minus 5 is not equal to 5 minus 10, right? Now, of course, 10 plus 5 is equal to 5 plus 10. That's the commutative property over addition, never subtraction. Oh, C. I didn't do C. Let's do C. So this one is 6a times 6a, which is 36a squared. 6a times negative 2 is minus 12ab. 2b times 6a is positive 12ab. Again, in addition, in mathematics, we tend to put things in order. Because if I wrote down 12ba, you might not recognize that that's the same thing as 12ab. So if we write them in alphabetical order all the time, we'll be able to recognize those like terms a little bit better. And then we say minus 4b squared. So what happens here is our middle terms cancel out, and we get 36a squared minus 4b squared. So hopefully you notice a little bit of a pattern going on here. And right underneath it, I have this little notice that says multiplying conjugate pairs results in the difference of perfect squares. Look, I'm a poet and I didn't even know it. Multiplying conjugate pairs results in the difference of perfect squares. All right, that might be a little thing to remember. So conjugate multiplication pattern. So here it is. So it's x minus a times x plus a gives me the perfect square, or that we call this DOP sometimes, difference of perfect squares. All right. And remember, order matters. So exercise 7 and 8, hopefully you're able to write these out pretty quickly because this is all review from Algebra 1. So x squared minus 9 is going to be x plus 3 and x minus 3. And of course you could say x minus 3 and x plus 3 because the commutative property says we can switch them around. Now this is what I'm talking about in B. Make sure that you're not falling into the trap of liking to put that variable first, because 4 is in my first position, which means its square root has to be in its first position. So minus x and plus x, because x times x is x squared. Now in 25, the first thing I might consider doing is looking for the GCF. So is there any GCF that goes into 4 and 25 evenly? No, there isn't. So, but in this case, 4 and 25 are perfect squares, so we can factor them. All right, so we get perfect. Double bubble. That's what my student teacher a couple of years used to call it. So we're going to do 2x in the first position, plus and minus, and 5 in the second position. We're just looking at square roots here. Same thing with D. Square root of 100 is 10 in the first position. Minus plus will be a little different this time. Now, what's the square root of x to the fourth? That's right, x squared. It'll always be half. So if I had x to the 10th, the square root would be x to the 5, x to the 5th. If I had the square root of x to the 50, that would be x to the 25. So it's always half of what the exponent is when you take the square root. And don't worry about fractions. Fractions aren't half bad, because here, again, they're perfect squares. X in the first position, plus and minus. I usually put the plus first. I'm a positive person, so I like the plus sign being first, but it doesn't matter. So what's the square root of 1/4? That's right, 1/2. Square root of 1 is 1, square root of 4 is 2. How about this one? I'm going to put it up here because I'm squishing down below. Again, first position is 25, so 5 goes in the first position, plus and minus. Square root of x squared is x, and square root of 9 is 3. X over 3. So square root of 4 is 2. Square root of 9, I'm sorry, square root of 81 is 9. X, 2 over 9, x. All right, I'll put the plus and minus this way now. And square root of 49 is 7. Square root of 9 is 3. Notice we don't really have to work with them that much. They look kind of nasty, but they're not too bad. All right, so how about this one? Square root of 36 is 6. X to the 4th power, take half of it, minus 7y to the 7th power, take half of it. Oh, I put plus, minus, and plus. Plus, I put minus and minus. I need minus and plus. Easy, right? I'm sorry this was a little bit long. I did two different situations. I did the GCFs and the conjugate pairs in one lesson. So, but I think you can handle it. Not that hard. So you're going to come into class hopefully and do that independent practice with your teams, and you're going to run through them really fast. Okay? So until next time, make good choices and be safe.